video, we're going to look at the concept called blackbody radiation. This is a paradox that scientists working in the late 1800s noticed that particular emitters, these were jet black cold metal that would not emit light, but when heated would start to emit solar radiation, or not solar radiation, but EM radiation that followed the solar radiation pattern even at a specific temperature of 5,250 degrees Celsius. And this spectrum, the solar radiation spectrum that you see on the left-hand side of the screen, is this little kind of gold-colored line that you see here. And you can see that if you take light from the sun, that the spectrum of light of wavelengths are in the infrared spectrum, the visible spectrum, and the UV. And most of the light that is in the solar radiation at the highest intensity is within this bar, or part of the graph, of visible light. And there is quite a bit of infrared light that you see here, but as soon as you move into the UV section, the light trails off dramatically. And it turns out that we could not technically understand mathematically what was going on here. And just so that you could see what I'm talking about whenever I'm talking about something that's black body that radiates, if you took a piece of metal, shown like over here in this right-hand side, and applied heat to that, it turns out that it starts to radiate light. And the hotter that it gets, the more light that it produces at a greater intensity within the visible spectrum, close to that kind of middle section where it ends up being yellow. And so if you remember that Roy G. Biv, you start to have temperatures that are lower in the R section, and then as you move up in that, you move closer to the Y. And so this is why you have yellow color versus red color down here. Red would be colder, yellow would be hotter. Now it turns out that that particular graph that's in blue is that black body. So this is if we had a particular piece of metal, we heated it to 5,250 degrees. If you notice, it tracks very well with the solar radiation spectrum too. But it turns out that we can actually look at the blackbody spectral radiation at different temperatures. And so we still have the same idea here of visible light in this little section here. Excuse me. Ultraviolet light to the left and infrared light to the right. And we have 4 different curves on here. One that is at 5,500 Kelvin, 4,400 Kelvin, 3,400 Kelvin, and 2,500 Kelvin. And it turns out that the light that is emitted in the visible spectrum will differ based on that temperature. And so something that is heated only to 2,500 Kelvin, its maximum wavelength of light that would be emitted would be in the infrared spectrum, where something that's heated to, say, 5,500 Kelvin, its maximum wavelength would be in the visible spectrum, somewhere in the kind of yellow section that you would see coalescing as the overall color of that substance. And I put over here on the right-hand side a kind of diagram that uses the temperature in Celsius, so keep in mind that Celsius and Kelvin in these two different diagrams, of what color you might see something heated at a particular temperature. Now, it turns out that we know that mathematical expressions were worked on and turned out that they could be used to explain why longer wavelengths showed experimentally what we saw when we heated substances, metals, black bodies, at particular temperatures. However, the mathematical expressions started to break down and not it showed like fairly large discrepancies when you started to look at shorter wavelengths. And shorter wavelengths are where you have the ultraviolet wavelengths. So we called this the UV catastrophe. And we couldn't understand mathematically what was going on. And then in 1900, a scientist called Max Planck developed an idea that would fit mathematically with the experimental observations. And what he used and decided was that the electrons within the atoms of the metals could only be located in quantized energy levels that he denoted with the following values. And we call these quantized levels, we use the variable n for those levels, and the levels are strict levels called 1, 2, 3, and so forth and on to infinity. But they could only be at these quantized discrete levels. And he was able to put them in an equation that related frequency and wavelength to energy, keeping in mind a constant that we now call Planck's constant. And this is what the equation looks like. E equals NH nu, where E is the energy of that particular wavelength. Nu, again, is the frequency of that wavelength. N is your quantized value, and it's going to be one of the values listed above. More often than not, when using this equation, unless stated, the value is 1. And H is the constant that Max Planck was able to figure out and put into this equation so that it would work to fit experimental observations. And so we call this now, just in his honor, Planck's constant. And this is also a value you should put in your toolbox, 6.626 times 10 to the minus 34 joules seconds. Now, I will say that Max Planck decided and developed this idea of quantized energy levels. However, he could never explain why these quantized energy levels worked, and that will be described in later videos when we start to talk about Albert Einstein's photoelectric effect, and we start to talk about Niels Bohr and the Bohr model, where they start to kind of fit together and explain how they work with respect to electrons in an atom. So this is where this video is going to end. We're going to not use this equation in practice examples. Instead, we're going to use this equation in the next video on the photoelectric effect. So I will see you there.